Today we're going to create a MATLAB function that will take the derivative of a function at a specific point. And we're just going to do this for the first derivative here. And let's begin by looking at the difference in the error for the backward, forward, and centered finite difference formulas. You can see that our error for the first derivative formulas here are proportional to h and h squared. If we go on to the backward finite difference formulas, you can see these are also proportional to h and h squared. But finally, the centered finite difference formulas are proportional to h squared and h to the fourth, so they're a little bit more accurate. We're going to use this bottom one here. Let's go ahead and switch over to MATLAB and get that going. Okay, now we are in MATLAB here, and let's get our function started. We're going to make the output capital D lowercase f is equal to, and deriv f, okay, will be the name of our function. You can see I already have this file named deriv f. And our inputs here are going to be a function f, the location that we want to find the derivative at, and then how small we want h to be. Okay. Now, we're going to make some further edits to what we're going to do here momentarily, but I just want to at least get us started here. Okay. So let's get that formula in there, okay, the formula for the derivative. So df would be equal to, and I want minus f of x, right? This is where we want to evaluate it at. But no, I want to be 2 x's over from this, because it's x sub I plus 2. So I'm going to do plus 2 times h. Okay? And then the next one will be plus 8 times f of x plus h, because we're at x sub I plus 1. We're only 1 x away now. And then minus 8 times the function at x minus h. Okay. And then finally, what's the last one? Plus f of x minus 2 times h. And we want to take this and divide this all by 12h. Now, this would be sufficient. We could just end this right here if we wanted to. But if we want to make this more accurate, we could use the Richardson extrapolation. Okay. Let's see what that is. Let's remind ourselves of what that little formula looked like. What we do is we have some approximation h1, and we multiply it by 1/3, and we have another approximation that is based on h being half of the original one, and we multiply it by 4/3, and then when we subtract these, it gives us a better approximation. Okay. Let's go ahead and code that in here. So we're going to have, instead, how about h1 is equal to h, and h2 is equal to h divided by 2. And then this can be df1, and this is going to be all based on h1s, okay, the spacing of h1. And then we can do the same thing, but for h2. So I'll just change this to df2 and change all these h1s to h2s. And we can go a little bit further. To finish this, we want df is actually going to be equal to 4/3 times this approximation using h2, so 4/3 times df2 minus 1/3 times df1. And let's go ahead and save this, and let's give it a test. Okay. Let's start off by taking the derivative of some function at a point that we can do really easily. So how about we consider the function x squared, and let's maybe take its derivative at, how about 5? Okay. All right, and we also need to specify an h. How small do we want h to be? Let's pick something small here. But let's think about what we expect this to be. Well, the derivative would be 2x, and then if you replaced x with 5, that'd give you 10. So hopefully this will give us something close to 10. Okay, and it is. Let's look at it under format long, because under format short, it looks exactly right. Okay, so that's pretty good. It's pretty good. Let's see how well this would work if we were to maybe try and plot a derivative. Let's maybe instead consider f to be sine, and let's actually plot it. So we'll use f plot, and then we'll have f comma the domain we would like, and how about 0 to let's do 2 pi, one full period there. Okay. And let's go hold on, and we'll do another plot here in a second of the derivative, but let's just make sure that this looks good. Okay, that looks good. And we know that the derivative should look like cosine of x, but let's use our derivative function to compute those values. So let me maybe say f prime is equal to, and let's make our variable x here. And we'll be plugging x into our function f there. Okay? So we're deriving the function f. And we want to be doing this at not a specific x here. I'm gonna change this to be just x. Let's go ahead and give it a run. So the only thing we haven't done is tried to plot it. Okay. And we'll use fplot again. And actually I just need to type in here f prime. Let's go 0 to 2 pi. Looks pretty good. Okay, that looks like cosine. And let's maybe plot cosine over that and see what that looks like. See if we can even distinguish between them. Okay. So let's maybe say g, specify the variable, and let's plot g over the same domain, 0 to 2 times pi. And let's specify the color here. Let's make this one black. That way we can see it against the red. Okay, if we even can. Okay, so we can, but can we see the red one is the question. Let's maybe zoom in, see if we can. Okay, so these are so close that we can't even distinguish between them. All right, and that is it for this function, deriv f.